So today we're going to unpack a problem that's right at the heart of finance, trying to predict when a company is about to fail. It's been this incredible 60-year quest for the perfect crystal ball, a really fascinating story of evolving ideas and tech. Let's get right into it. Just think about it for a second. What if you knew with some real certainty that a major company was right on the brink of collapse? The ability to answer that question is the holy grail. It's worth billions. And for decades, the absolute sharpest minds in finance have been chasing a definitive solution. All right, so our story really kicks off in the 1960s. Before this time, figuring out if a company was in trouble was pretty much just gut instinct, right? A kind of feel for the market. But that all changed with the very first formal statistical attempt to actually crack the code. So, in 1968, along comes this professor, Edward Altman, and he has this totally revolutionary idea. He completely reframes the problem. He basically said, forget gut feelings. This is a classification problem. He treated healthy and bankrupt companies like two totally separate groups and then used data to find the mathematical line that best separated them. And this is what he came up with, the famous Z-score. Now, don't get hung up on the math here. You don't need to memorize it. The really crucial point is that this wasn't just some random mix of numbers he cooked up. It was a statistically derived recipe, a very specific, weighted combination of 5 key financial health indicators. And what's so cool about this is when you break it down, the parts actually make a ton of sense. You've got liquidity, that's like a company's cash on hand. You've got profitability over time. And then there's operating profit. That's the big one. You can see it has the highest weight in the formula. It's literally like a doctor taking your blood pressure, your heart rate, your cholesterol, and combining it all into one single health score for the company. But here's the catch. The Z-score, it had this one big fundamental problem. It gave you a score, a number, but not a clear answer. Okay, so you get a score of 2.1. What does that actually mean? What's the real chance of failure? Is that twice as bad as a 4.2? The model just couldn't tell you. And that gap, well, that created the need for the next great leap forward. Okay, so that brings us to the next big evolution. The goal wasn't just to make the score better. It was about changing the very nature of the answer itself, moving from some abstract number to something way more useful, an actual probability. So in 1980, this guy, James Olson, comes along and uses a technique called logistic regression. And wow, was this a game changer. It totally shifted the question from Altman's, hey, which group does this company look like, to the much, much more powerful question, what is the specific percentage chance this company will fail in the next year? So how on earth did it do that? Well, the secret sauce was this brilliant mathematical trick called the sigmoid function. It looks like a stretched out S. What it does is it takes any score, doesn't matter how high or low, and just elegantly squeezes it into a value between 0 and 1. And boom, just like that, you can talk about risk in actual probabilities, a language that, bankers, investors, regulators could actually use to make decisions. But of course, the story doesn't end there. Even this awesome new model had a major blind spot. Both of these early models were totally static. They took a single snapshot of a company's health, usually from an annual report. It's just one picture. But we all know failure isn't a single event. It's a process, right? It unfolds over time, which leads us to our next major chapter, adding the arrow of time. The idea was to stop looking at companies like they were static photographs and start seeing them as moving films. Fast forward to 2001, a guy named Tyler Shumway makes this really smart observation. He brings in something called a hazard model, which was actually being used in medicine to predict patient survival. The question was no longer just, will this firm fail? It became, okay, given this company has survived up until today, what's its risk of failing in the next year? It's a subtle but crucial difference. And honestly, this was a huge shift in thinking. For the very first time, these models could use a company's entire history, its whole trajectory. Is its profitability trending up or down? Is it taking on more debt? This dynamic view made the predictions so much more realistic and way more powerful. Okay, so let's recap. We've got probabilities, we've got time, but the real world, it's messy. It's complicated. Relationships between financial variables aren't always nice and linear, and this is where the machine learning revolution just blows everything wide open. So first up in the ML world is the decision tree. The easiest way to think about this is like a game of 20 questions for companies. The algorithm learns the best possible series of simple yes or no questions to ask about a company's finances, like is its leverage over 50%, to eventually get to a final prediction. It finds these thresholds all on its own.
Now, the great thing about a single tree is its power to find these really complex, non-obvious patterns. But, and this is a big but, it has a huge weakness. It's super unstable. It's kind of like relying on one very smart but very moody expert. Just a tiny little change in your data could create a completely different tree with a totally different prediction.
So, what's the solution? Well, it came along in 2001, and it's just brilliant. The idea is simple. If one expert is moody, don't ask one expert. Ask a whole room full of them. A random forest builds hundreds of slightly different trees on different pieces of the data, and then just lets them vote on the final answer. It's the wisdom of the crowd, and it works incredibly well to smooth out that instability. But what if you could do even better? Instead of a crowd of experts all talking at once, imagine a single student that gets smarter and smarter with each pass. That's the core idea behind gradient boosting. It builds one tree, sees what mistakes it made, then builds a second tree whose only job is to fix the mistakes of the first one. And it keeps doing that over and over, building this incredibly strong chain of models. And this whole idea of boosting gave us what we call the big three algorithms that pretty much run the show today. You've got XGBoost, which is kind of the all-around champion, the powerhouse. You've got LightGBM, which is built for insane speed on massive data sets. And then there's CatBoost, which is a genius at handling messy categorical data like what industry a company is in. They're the peak of predictive power. But all of this amazing predictive power, it came with a price, a big one. We had built these prediction engines that were unbelievably accurate, but we couldn't easily see how they were making their decisions. We had accidentally built these incredible black boxes. And that brings us to the final frontier in this whole story. And this quote just nails it. This is the central tension in modern finance. I mean, think about it from a regulator's point of view, or a CEO's. Can you really bet the company on a number that comes out of a box you can't understand? That's not just an academic question. It's a huge real-world problem. So right now, there are basically two big approaches to solving this puzzle. The first one is to keep the powerful black box, but use another tool like something called SHOP to sort of peek inside and explain its decisions after the fact. The second path is totally different. It says, hey, why don't we just build a transparent model, a glass box, from the ground up? And models like explainable boosting machines can do just that with almost the same power as the black boxes. And this all leads us to the huge, defining question for the future of finance. This 60-year quest has brought us to a crossroads. To keep our financial system safe, what do we value more? A near-perfect prediction that we can't fully explain, or a really good prediction that we can understand completely? The answer is going to shape everything.